Today, I am very pleased to welcome Fidele Mazimpaka, our UMass campus energy engineer. Mr. Mazimpaka has a bachelor's degree in electrical and electronic engineering and a master's degree in engineering and industrial management. With over 20 years of experience in the design, the development, and the implementation of energy products, Mr. Mazimpaka's skill set in project management and building operation management is unparalleled. His expertise includes heating, cooling, and ventilation systems, building automation controls, on-site power generation, central plant design, renewable energy installations, real-time data collection and analysis, facility management, measurement and verification, and risk management. The problem with asking Mr. Mazimpaka to present is to decide on which of his multiple expertise that we would like him to share with us. So perhaps you've wondered how UMass's 38,000 occupants, you included, located in over 13 million square feet of buildings with multiple mechanical systems of assorted vintages, keeps us reasonably comfortable throughout our seasonal variations, or perhaps not. Either way, Mr. Mazimpaka is here this evening to fill you in. Please welcome him.
Thank you, Carl. Thank you for the longer presentation on my background. Although I'm a little bit nervous, I don't present in front of a large audience. Thank you for joining, and it's going to be hard to keep you awake for more than an hour after a long weekend. I'm on a Monday, but I'll do my best. I've been invited to present on the building automation system, and I don't know how many of you are familiar or have touched or used the building automation system. If there is any who has got experience with building automation, raise the hand. Very good. 1, 2, 3. So my presentation will be probably for everyone just the introduction to building automation system, so that most of the people here can understand, the components of a building automation system, how it works, and after the presentation, we will log into UMass system and show you how we use it on an hourly basis, on real time, and we can look at this building, we can look at the chiller plants, we can look at the other buildings, and I can show you different components, how they work together. Is that fine?
Guys better now?
Okay. Great. So, the learning objective here is to introduce you to the basics of the building automation system and use the building automation system actually to optimize energy consumption and building performance. Because these systems are not that cheap, so if you don't use to generate or save money so that they can pay themselves, it's not worth using them. And also see how they help us design for high efficiency and how they can improve and increase the equipment life cycle costs. Lastly, we'll see how we use data analysis for troubleshooting and malfunctioning equipment. Okay, I think we use the button. So let's go through the definition of building automation system. It's not changing.
Not changing.
Okay. Quick definition of building automation from Wikipedia. The building automation is the automatic centralized control of a building HVAC, which stands for heating, ventilation, and air conditioning, electrical, lighting, shading access, control, security system, and other interrelated systems to a building management system or a building automation system. The objectives of building automation systems are improving occupancy comfort, efficient operation of building systems, reduction in energy consumption, reduce operating and maintaining costs, and increase security, plus historical performance documentation, remote access control operations, and improved life cycle of equipment and related utilities. So that's a long definition. But we'll go through each of them and see how it does help. So first, let's look at the occupants comfort improvement. Like we are here, our comfort is mostly temperature. The other thing is relative humidity. Even though it was comfortable, if it was foggy and too humid, you would be uncomfortable. The other thing is indoor air quality. If it was just 70 degrees, we have good relative humidity. If the air was stinking, it won't be stinking here. The next one is safety. And this applies mostly for labs here, because most of the labs generate lots of fumes. You have to exhaust those fumes, and so you have to make sure that when you operate in the lab, nothing comes back to the operator. Everything has to go through the exhaust. So that's where ventilation comes to be very critical. And also, there's parking garage. You've been to campus parking garage. What do we do with the equipment? Drive through. What do we do? We track the CO level, carbon monoxide level. If it does go up, we have exhaust fans that start to bring in more fresh air to dilute them. Those are a few features for safety. The next one is equipment performance. Can you imagine if you had all your equipment running 24/7 or year-round? How big would be your bill? Let's take your home, for instance. If you're not there, nobody is in the house, it's good to lower the temperature in the room, and also increase it when you're in. So if you had to run it 24/7, guess what? The bill would be huge. Same as here on campus, we try to start and stop the equipment based on the occupancy, whenever we can. The next one is load control based on demand. Sometimes, we may have huge demand, summertime for instance, if we are cooling and the temperature goes from 60 in the morning to 95 degrees, we have to be able to ramp up our chilled water systems so that we can satisfy the demand. And vice versa, when the temperature goes down, we lower the speed of we decrease the flow of the chilled water so that we can meet the demand. The other thing is lead lag and equipment operating systems, so sequencing. What happens is, just an example, if you have 3 pumps, if you have 1 pump running all the time, guess what, the other 2 are not running. After a certain period, that pump is going to burn out, and then you have to start the other one. What we do alternate them so that they don't wear. You don't put pressure on one and don't wear the other one. So we alternate them so that they have equal time of operation. Those are a few things the system does. The other thing is reduce maintenance cost. So maintenance is based on run hours. Okay, so if an equipment is built to run 20,000 hours, you can say, I'm going to run this equipment for 5,000 hours for 4 years, or you can run it 8,700 hours per year. That would be three years. So the longer you run them per day, the less life expectancy you expect from it. And vice versa. The other feature is the remote access and control and operation. This is a big asset with the building automation system. Imagine if every equipment we have here was being operated manually, like it used to be 50 years ago, 75 years ago. How many people would we have on a campus like this? I think we would have 2 or 3 persons per building just to operate the equipment. That would be probably 600 people just to operate the equipment. But what we do have, the advantage we have here, with the remote access, you can just control the equipment remotely without even being here. So that's a huge reduction in labor cost. The other thing is when you reduce the cost of operation, you increase the life expectancy of the equipment and also you improve your life cycle, the life cycle of your equipment. Troubleshooting. I'll show you how we use the system on troubleshooting the equipment. Mostly, we have an alarm system that allows us to get notification when an equipment is not running properly or when it's failed. And also, we have a built-in system so that the equipment can shut down to avoid catastrophic failures. For instance, if it's, let's say, minus 20 degrees, and you open a dump of an air handling unit, and you have cold air running through a coil, and that coil doesn't have enough hot water to run through, guess what? That coil may freeze. If it freezes, it bursts. When it bursts, guess what? You have a flooding. You have a major issue. So our building automation system is a feature that when there is a low temperature alarm, it sends notification to the system, and the system closes the dampers, prevents air from coming from outside, and then it blocks the airflow through the coil, and then the coil can survive. That's an example. If I take chillers, for instance, some chillers may be running with a high condensed water temperature. So what it does, it may damage the chiller. So when you have high condensed or hot water temperature, coming back to the chiller, you may stop the chiller first and send an alarm. And the alarm will be just check the condensed water temperature. And the chiller won't start until you fix the problem. So those are a few things that we have in our system to prevent equipment from catastrophic failures. The last one on the list is energy management system. This is a big asset. This is I would say, building automation system. Most of the campuses and the large buildings call it energy management system because it drives the energy consumption and the utility consumption. Just an example, when on Thursday, for instance, nobody was here. There were a few people. Okay, what we do is we turn off the equipment just by clicking on a point. We go and schedule units to be off. Okay, you maintain a certain temperature, let's say 60 degrees. Instead of bringing outside air, heating and maintaining 70 degrees. So just by doing that for 60 buildings, you can save probably 20 to 30% of the energy consumption on campus. So let's look a little bit at the components of a building automation system. I put together a small graphic, and I'll start from the bottom. So when you look at this here, I have N devices. N devices can be a temperature sensor, the monitor on the wall, can be a pressure sensor, can be a valve position, can be a damper position, can be a chilled water flow rate. So you have all those points, you call them points. Those points, you collect them, and they report to a kind of a supervisory controller. Well, it's called a field controller, it's not a supervisory, but they report to a field controller. So the field controller is a small controller here. It may have 16 points or 24 points, depending on the size of the controller. So you can collect 24 points. But 24 points in a building, it's not that much, because if I look at this room, for instance, you may have 4 or 6 devices already, and each of them may have 6 points. So that's 24. So you may have 2 field controllers in this room, and most of the field controllers then report to a main controller. The main controller is large. It can have between 2,500 points to 5,000 points. So these field controllers dump all the information into a main controller. And the main controllers, you can have 1 or 2 per building, depending on the number of points you have in a building, and depending on the size of the building or the size of the equipment. And then the main controllers report to an application and data server. Here on campus, we have 1 large data server that helps us control all the main controllers on campus. And then you access it through a user interface system. Now, to make it a little bit sophisticated, this is a system we have at UMass. For instance, and this is just another Metasys network. I copied from Johnson Controls because we use Johnson Controls here. You can see we have user interface. User interface here. We have our server, and we communicate to our main controllers through Ethernet and IP addresses. And these main controllers communicate to field controllers through different backnets, MSTP, which is master, slave, token passing. It's too hard. You won't have that in your quiz. Okay, and they communicate by a different communication mode, but it depends also on the age of the equipment, because some may be MSTP, some may be M2, but all these report to the main controllers, which reports to this main server. Next. So, quick explanation on how they work. The main controller is used for one building, or one site, or one plant. You can have a main chiller, larger chiller plant, or large power plant. So, or you can have a main controller. Depending on the size of the building or the size of the site, multiple main controllers can be used. Main controllers can also be used for one large piece of equipment. Field controllers are used on one large equipment or on a small building or site. And the devices examples are temperature sensor, relative humidity sensors, CO and CO2 sensors, occupancy sensors. We may have some here, probably.
Yeah.
Yeah, over there I can see one. That may be another one. Valve position, because you may have a chilled water or hot water, so you want to modulate the valve position to control your temperature. Air flow rate or water flow rate, on-off status of equipment, mirror readings, pressure differential, voltage, amperage, kW, pressure, damper positions, and so on. So the building automation system is usually configured for remote access to minimize labor cost, we talked about it, and improve efficiency. Main controllers and field controllers are also accessible locally or remotely. For technicians to troubleshoot them when they are in the field, they can connect directly to the field controllers or to the main controllers and look at them, but remotely you can if you're in the field. So now I'm going to switch to the UMass Building Information System and walk you through some examples. We will look at some buildings, how they work, and a review of the field controls, the main controls, show you the points, show you the end devices and how some buildings operate in real time.
So we got to switch computers now. And the reason is I have Metasys on my computer. But the Metasys I have is like a gun that just shoots blanks. I can't do anything. I can look at things, but I can't do anything. This, what you're going to see, is a real gun.
There's no power.
Yeah. We're gonna just move you.
Okay.
So we're going to move you over to this one.
Here?
Yep.
And then share screen.
Share screen?
Yes.
Okay. So, this is our user tree. We talked about the main server. So you collect all the information from different field controllers. You will report to a main controllers, and the main controllers will report to main server, which is here in ADX. So I'm going to write these. So these are our, if you look at this, you know, these are our main controllers. Design building is somewhere here, but if you look at main controller 8, for instance, it's finance. Main controller 7, it's the ISP chiller plant. And I'm going to take an example on this one, for instance. This one, it has a program for each feature, but when I look at how many field controller it has one for the chilled water pumps, one for the cooling towers, one for the chiller control itself, one for one tower variable frequency drive pump, another one for the pumps, another one for the pumps. So it has probably 7 or 8 field controllers. And if you go, you open those field controllers, you want to see how many end device are in the field controllers. Here we are. So we have a chilled water temperature sensor here. We have a differential pressure. It tells us how much pressure we have for the chilled water coming in and going out. We have a pump command, for instance. We have a speed. So if I highlight this, you can see the ones we have here, and I'm going to show you which one, what they mean exactly. And you can see the values. So it's a chilled water plant, real data here. For instance, we supply chilled water at 53 degrees to labs on the northeast side. ISB, LSL, Skinner Hall, including this building, Worcester Dining Commons, Franklin, and ILC, and Hasbro. So this is the chilled water temperature that's being supplied to them because it's cold enough, so we don't need to cool the water temperature. But again, if I go back in history, for instance, which I can do, I can show you the temperature, how the temperature sometime in August or July, so I can take you back to even 4 or 5 years ago. You can see the chilled water temperature here. I'm going to log in to show you a trend of temperatures we have. Like now, you can see this morning it was 10 a.m. it was hovering around 51. Now it's up a little bit. So if I want to go in history, tell me, when was your birthday? September. September. Okay, so let's go to September and see. Now we have 51 degrees. We go back to September. So I'm in November here. I can go back to September 1st through end of September. This is November. Okay, we can see how we're doing. Can you see the screen, all of you? Okay, so you can see the chilled water temperature we're providing to the buildings was between 46, 45, 46 degrees, and sometimes it would spike to 49 and come down a little bit. Okay? Who can pick another date?
October?
October. Oh, it's close to September. But you can do it. Let's look at October. So you can see September it was between 45 and 46 average. If we go to October, I can go to October 1st through end of October 31st. Let's see how it goes on. Still, it was still warm. Okay. It's got a different date.
April?
April. Oh. Okay, April, let's see April. April. Going back to April. I can pick April. And I can go April and May at the same time. Through May 31st. Let's see. It's going to be a little bit different. You can see it was doing 45. Some days, it would go to 51. And this line here, these are issues you may have. It was unreliable. When it's unreliable, the last value that was in the system keeps reporting that value until you fix the system. Sometimes, the controller may be stuck. And when it's stuck, it's either unreliable or it's offline. You have to go back and repair it. So it was around 45. So April, you can see here, went through a hiccup, went from 45, 46 to 51 for 2 hours. Any other date? Okay, I think we're done with this. So
what would the spikes in water temperature indicate?
can be due to many issues here. Sometimes it may be a power failure, or the chillers are not running properly, or you may have pumping issues, because when you have a pumping issue, for instance, instead of delivering a larger flow, you deliver a lower flow. That flow, if you have a lower flow, you may not, the water you're providing is not heating up properly. So those are a few things. Or it may not be a problem if the outside air temperature was reasonable. But another thing I want to check is probably, was this Labor Day? No. This was a problem. It's not a problem. But if it's 51 degrees, it's not that critical because we're not worried about it until it gets to 55, 56 degrees. When it's 56 degrees, then we have to alert, to get an alarm and do an correct issue. Otherwise, if it's 60 degrees, we may overheat some equipment and damage them. So this is a user tree showing each main controller, and we went through the main controller, we went through the end devices. Now let's look at the graphics now, because now you just see this trend error. I want to show you a better improvement for this chiller plant. So we looked at this chiller plant. I want to go there. It's this one here, ISP chiller plant. And we can look at live how it's working. So this is way much better, actually. So here I can see how many chillers we have running. The chillers tell you which one is enabled, but it tells you also which one is on. So based on the flow. So here based on the flow, I don't have any running. But I'm not worried too much. Why is that? It's because my temperature outside is 28 degrees wet bulb. So what you do, you don't need to run a chiller where you can have a free cooling. So what we do is circulate water to the cooling towers. So the cooling towers cool that water, we bring it back, we give it to the labs, and our supplied chilled water here is 55 degrees, and you have it returning at 58 degrees. Perfect. So those are the features of a building automation system. And it's done automatically based on outside air temperature. Now let's look at the design building, because everyone wants to know what's going on here. Okay, design building, let's look at the floor plans, okay? Which room are we in here? 170?
Yep.
Okay, so this is the first floor. I look at 170. Here, 170, indeed, if you look at the ceiling, you have two sections here. I have one here, another one. It's probably what we have there. So I can look at one section here of 170. What do we have? So sometimes it can be slow. So we have outside air coming in. We have the damper that's open 100%. It's supposed to supply us air here. It's taking time, I hope. So we have the set point here is here 625 CFM of outside air. So hopefully it's going to start soon. And then the damper is open 100%, which means it should be supplying the maximum capacity. And then this fan coil unit here, you can see this is supplemental. We have air coming in, but this one here kicks in only for heating or cooling. So if, for instance, the thermostat we have here, which is set to 68, you see? You see the thermostat at 68? Okay, so can you follow my cursor here? So the zone temperature is 68.9. And the thermostat is set to 68, which means it's satisfied. It doesn't need heating or cooling. So if it does, the fan coil unit doesn't kick in. So we don't need heating, we don't need cooling, so the unit is satisfied. Let's look at the other systems we have here. So we looked at the first floor. Let's look at the air handling unit.
So maybe give them just a little bit of orientation of where this equipment is. It's very close to you.
Yes. Thank you very much for that. So thermostats. We have temperature sensors right there.
Yep.
Okay. We have a temperature sensor that one senses the temperature in the room. And we have air supply here, if you look at the cursor here. So it's just one drawing, but we have multiple diffusers. So those are the diffusers here, which bring in air. So we have supply and return. And to be honest with you, I can't tell you which one is return, which one is supply. But we have supply and return. But in this case, from what I see, just supply here, and return may be or hidden somewhere else. I have to try to find it. Okay, but this may be only supply.
Yeah, I think returns are up above the funnel.
Correct.
Above the drop ceiling rather, in the funnel.
Correct. So the coils are hidden. I don't know if you can see over there a silver or dot. Okay? So usually they are somewhere in the duct wall. And you have a valve here, a valve that opens and closes. Closes based on the demand and based on the temperature request in the room. I can't guarantee that it's gonna work, but let me see if we can override these to 72 degrees and see if it's gonna keep it. I can't guarantee it's gonna work. Override these. 74 degrees.
See, this is what they don't let me do.
Okay, it's starting. Fine starting.
Yeah.
That's a good news. There you go.
Yeah.
And you can see the heating coil. It's red and it's 100%. So it's cooling, it's taking the air and it's preparing it and heating to maintain to get to 74 degrees. And you can hear it.
So that's the reason that we have a drop ceiling here. That's an acoustic buffer. So because clearly you want to hear what's going on in the space from the people, you don't want to hear the mechanicals. When we get over into the studios, although when you enter the studios, you see there's a low drop ceiling. That's where fan coils and things are that make some noise. But then as you move out into the studios, you know the acoustic ceiling disappears. And we're looking at the underside of the CLTs above, which is part of the pleasure and the beauty of the building.
Okay, I don't want to work with so here I put in an override to 74, you can see it's running. If I take out the override, here, go back to normal, release the override, and fan is going to stop. Give it a minute, you'll hear it. So, look at the handling units. The water systems here, for instance, for the design building. We have hot water systems. Again, this is a graphic for hot water system. So, what happened, we have a PRV system. So, let me go back a little. We have steam coming from the power plant. Usually the power plant sends it either is a high pressure, medium pressure, because high pressure is over 400 or 200, but it's medium pressure, which is 90 psi. So 90 psi is a lot. It gets reduced to 15 psi so that you can be going to some buildings. So we have it supplied to 9.16 psi, you can see it here, and this is the flow of the steam. So steam flow coming into the building right now, it's 475, and it enters at 16 psi, but it's reduced by the pressure reducing valve to 9.7 psi. Then the steam goes through a heat exchanger. It dumps all the heat into an exchanger, and you have the hot water coil that picks up that heat from the steam and translates it into, it takes us that heat and heats up hot water. And that hot water is circulated to the building. Right now, if you can see, we have hot water supply at 160, right there. And the return is 140 degrees Fahrenheit. And then you have two pumps. Always one pump for redundancy, just in case one fails. You don't want to, if one pump fails, and you have 20 degrees outside, guess what? You may freeze your cores. If you freeze your cores, they may burst. Imagine a building like this. I don't know how much it costs to build it. How much will it cost? 15, $20 million. All of a sudden, you have it flooded. You have to clean it. You're losing $2 to $3 million. If nobody is there to stop the flooding right away. If it's over the weekend, it can be very costly. So that's why you have two pumps in case one fails, the other one picks up right away, and vice versa. And also we have alarms on these pumps if there is no flow. We send an alarm to physical plant, and physical plant has to take actions right away. But those are the features for this the building automation system. I can switch this pump, I can turn this off and turn this on, and vice versa. The way they operate here, you have a lead lag system. So now pump 2A, B is in lag, and 1AB is in lead. This is the screen that shows us the lead and lag. Another thing too is for the hot water temperature, if it's 60 degrees outside, you don't want to supply 180 degrees. It's too hot. But if it's 0 degrees outside, you want to heat your building quickly. You want to give it a higher temperature. So here's a temperature reset here. It tells us, low set points, high set points. So if you look at it, if it's 15 degrees outside or below, you have to provide 180 degrees of Fahrenheit hot water to the building. And if the temperature is above 55 degrees, your hot water should be 140. Like usually after 55 degrees, the pumps turns off, the pumps turn off, and you don't need to supply hot water, you can cool more. So when you're in between, then your temperature will modulate based on outside air temperature. That's how you optimize your heating system. And also you avoid overheating or having those hot air blasts at once when the temperature is 180, and also you don't want your vacuum to keep hot. Another feature for this system here I'd like to share with you what we do for this building actually. We talked about energy saving, energy building, energy management system. This is one of the indicators for we have a steam meter here. We look at it and see how we've been doing recently. So I can go here and view train data. So this is how we've been modulating our system for the last 12 hours. So for the last 12 hours, you can see it was using 160 pounds of steam. And all of a sudden it went to 840, that was at 6:30. And then it went down, and then it's been going down. But the reason it went up, probably, okay? We look at the trend there. It's because, it may be because, you know, we don't start the IMM unit till 6 in the morning. So, that's one picture. I want to use this to go back to the system itself and see here and look at the trend data. The trend data and see how we've been doing over the last 7 days. Then it will give us a good idea of how we're doing here, if we really setting back the equipment at night or not. So this is my steam flow mirror. I want to go back to the trend data. I want to see how much I've been using over the last 7 days. So, go back again. I want to count these. This is here Monday, so let's go back to the 21st. So that will give us 7 days. Okay. That's not bad. So it shows that, you know, in between 0 here. So what time did we have 0 between, let's say, 8:30 p.m. and 6 a.m. So when you have peaks here, it's 6:15, 6:30, 6:15, 6:30. So that, and if I have this, I need to go back. I want to check how the building is operating now. So that makes me curious. While we go through there, I want to show you how I can check at 6:15 what's going on. So each air handling unit has a schedule. You schedule them to turn on and to turn off based on activities in the building. So let me take HU1 for instance. So this is the schedule for HU1. Today, it's supposed to run from 6 a.m. to 21, which is 9 p.m. If I go back and look at its weekly schedule, this is its weekly schedule. So 6 a.m. to 9 p.m. Monday to Friday. If I look at HU2, it should be almost the same. Maybe not. This one runs through Sunday. It's because it does supply that lab, air to that lab that's used during the week, over the weekend too. So this one has to run 6 a.m. to 9 p.m. every day. But HU3, which serves the main entrance, it runs 6 a.m. to 9 p.m. every day, Monday through Friday. So this explains why you have those spikes, because you have all the equipment starting at 6. They go, you know, you go from 60, let's say 62 degrees. You want to supply, you know, you want the room to come to 70 degrees before students walk in at 8 o'clock. Guess what? You're gonna have that, you know, that need of steam, that high need of demand of steam, so that you can be able to heat your building. I'm going to be respectful of your time here. show you one of the last features we use for energy management system, which is a good feature here. It's very automatic to a point where during the summer, for instance, or during the winter, we may get a call from the utility company. And the utility company would say, well, we don't want to put lots of pressure on our grid because we may run out of electricity. You remember in California last summer, and if you're around in 2004, that big power outage, that went for the whole Northeast and probably half of the Midwest because of the high demand. So nowadays, utility companies, would ask you to curtail. So we have an agreement with the utility companies that, we can curtail our electrical consumption. And what we do, we build into a system that can go into our building automation system and it can tell you what to do. So I'm going to show you what we built in. I won't turn it on because I don't want the power plant to be after me. Those guys are big and they can run. So what we do here, we have multiple stages. So what we do is when we get a call to curtail our demand, our electrical demand, folks at the power plant, they just go through this button here, they click on yes, and all of a sudden, when they click on yes, we use stage 1 and 2. So stage 1, it looks at every non-lab building, and it does slow down their handling unit. And it looks at those buildings too, it reduces the static pressure. And stage 3 is very critical because we don't want to touch very critical buildings unless it's 1 or 2 times a year when the temperature is above 95 degrees and our electrical cost is going to be way, way high. Sometimes you can pay up to $50, $60 a kilowatt to demand, while regular demand costs are 14 or 15 kilowatts. So you can triple or quadruple. And the other incentive we have to is when we do the curtailment, we get the kickback. Sometimes it can be $500,000 per year, it can be up to $1 million per year. So we are incentivized to help them. Plus, we generate our own power. And if we have control of this, a few times a year, we can generate money for the university. So what we do here, we go into this system, and you can select which chiller we want to run. Sometimes we may run absorption chillers instead of electrical chiller. Electrical chillers use electricity. Absorption chiller use steam. And in the summer, we have the capability of generating steam. So we generate more steam, even though it's a little bit expensive, but for that short period, at least our demand cost is maintained at a lower level. And another thing too is we slow down the pumps that feed larger buildings that have to run, mostly the labs. So when we slow down, when we reduce the differential pressure, we have a lower flow. You still have flow in the coils, but because you have a lower flow, you increase the temperature in some spaces by 1 to 2. That's very good enough. Sometimes when I look at the whole trend data, we can shave 10% or 15% of our electrical demand just by doing this. So this is a feature that was easy to implement. We spent $50,000 to have it done, and we had to pay back less than 3 months. So that said, I'm going to open up to questions. Yes, please.
I'm curious about the changes that occurred in the BAS in March of 2020, as a result of all the students going home and the system being changed.
That's a very good question. So March 20, 2020, what we did, we set back the temperature in those buildings because we were heating more. So, but when you set back the temperature, we didn't even have enough people here. We had just the essential people, and they were mostly very limited in number, probably 1 or 2 trades only per day. So what happened remotely, we set back the temperature in the spaces, we did monitor the temperature. So in this, but we didn't want to turn off everything, because if you turn off everything, guess what? You may freeze a coil and nobody is around. And when nobody is around, guess what? If you freeze a coil, water keeps coming and you may flood the whole building. So what we did was just set back the temperature to 55 degrees to avoid any issue, and then we were able to save a lot of energy. Plus, the good part was not only that. When you have equipment running, you have to have people maintaining it. So when we set it back, at least we have less equipment running. And April through June was good. Also, one of the other things we're doing was to run the, after we went through that cold weather, we could turn off some equipment. But we didn't want to turn them completely for a long period, because what happens with relative humidity, you can build other air quality issues. So we were flushing them twice a week. So you would run the equipment, the handle units, for 5-6 hours twice a week, so that you can get fresh air in the building and exhaust anything that may be accumulating in the building. That helped us save energy. Right.
With like such an extreme and unexpected shift, what of the system did like the BAS do automatically, and what needed to be done manually? Sorry, what part of that shift did you need to do manually, and what could be done automatically?
So what was done automatically was scheduling it. So when you schedule it, I showed you a schedule here. Let me show you a schedule, design building, for instance. It's 7. I go into here, I have the schedule. I take 1 air handling unit, for instance. It's running from 6 a.m. to 9 p.m. So I would go here and change it. Go to the Sage or edit this. And I can say, okay, I want you to run from 9:45. Monday, so I want to touch Monday. Let's look at the other one. So I say I want you to run from Wednesday from 9 to 1 p.m. That would be good enough. You bring in fresh air, okay? You flush the building and you let it rest for 2 days and you flush it again. That way, you keep it, you keep it healthy and you spend a little energy. So you schedule it manually, but did you see how long it took me? Yeah, and also for temperature setback, that's easy because I can do a query here. If I do a query, so I can go into one main controller here. I can do a query and look at how many. I can look at each zone temperature by just doing a query here. So these are the zone temperatures I gave. For instance, some are replying, but for the zone temperatures for design buildings are here. And I can look at those set points. Doing the same query. So once I have the set points, I can go here in these values and change the set points. So all of them at once. Any other question? Yes, sir.
Yeah, are most of these systems still acquired under performance contracts? And are there any trends towards open systems instead of just Johnson controls?
Yes. So there's no performance contract with Johnson Controls now. Johnson Controls had a performance contract with UMass in 2005. It was just implementing some energy conservation measures. When they were done, they were done. However, we buy Johnson Controls product and we use them, we use Johnson Controls for installation. And sometimes, for service when we need them, when we need their expertise. And you may ask me, why don't you have other systems? So, the reason is, we may want to switch to other systems, but you will learn that there is a cost of conversion. So if we have deep pockets, we would take that adventure. However, given the size of the university, given all the needs, there are more students who need scholarships. We have deferred maintenance that we have to address. So if we have to use other products, it may cost us more money than using the same products. So that's why we prefer to use Johnson Controls so that we can be consistent. We have more parts in stock, and we have to even our technicians, they are used to use Johnson Control system. We don't need to use three or four vendors, especially these controllers. Each company has the way they set up their systems to talk to each other. So when you have multiple systems, they may talk to each other, but you need a kind of translation, and there's a lot of lost in translation, and it can lead to lots of issues. So that's why we prefer to use the same Johnson Controls. However, we try to beat them up to get better prices. Yes.
Are there any open standards platforms? Because this has been a problem for decades that, you get locked in one ecosystem.
Yes, there is an open standard platform for new equipment. However, again, the integration of the systems into the platform we have today is very costly. Yes, Scott.
I have a few questions from the Zoom world. The first is, how is the BAS insulated from potential external viral attacks?
That's a good question. We rely on our IT department to insulate us from that. The good part is we are not at a very high risk, because if you turn off a building, it's less dangerous than turning off a nuclear power plant. You turn it off, we'll catch you the next day, and you can see who ran into it, and our IT department may do a search and find it. So that's the beauty of the building evacuation system. We haven't had any issues so far, so close to our IT.
Okay,
Another one?
sure. Which utility agencies offer the rebates for the installations, energy or water?
Energy for sure.
Yep.
Water, we have a contract with, we buy water from the town of Amherst. We have some negotiating deals with them. When we conserve energy, they give us better deals.
Mm-hmm. Okay. I have one more unless other
Please.
people have. Are these monitoring devices wireless?
I would say 99.9% are not wireless.
Hmm.
Our IT department is working on a protocol for wireless devices, but so far they have not recommended that we use wireless devices for security reasons.
Okay. Okay.
Any other question? Yes, please.
So with all that data, that lends itself, of course, to big data analyses, artificial intelligence, at least maybe not running the system, because we might not trust that. but at least analyzing it? Are you doing anything in that field?
That's a very good question. The system, the BAS itself has some features that can do a kind of prediction of space behavior or equipment behavior. Let's say if you have classes in this space most of the time, so it may start earlier to preheat or pre-cool the room based on the schedule you have. So they do adapt to your schedule. But that's all a bit of far ahead of ourselves. But it does have that feature. It's not the greatest feature, and sometimes, we try to make sure that, to provide you comfort. We don't disrupt any class, and we don't want you to get it. But I see it coming soon. In 10 years, it will be there for sure, or less.
All right, so I think we'll close up our lecture. There we go.